So, back to calc. We were working on our limits, and we have had the limit laws that essentially tell us we can just plug in x when.
Whenever it's a polynomial.
And when the rational is not make a zero denominator zero.
Okay, good. So that has saved us a lot of time on the 10 problems that you could do it on, where you just had to plug it in. If it's just a constant, there's no x, so the limit is the constant. But we had cases where we couldn't just plug in because our denominator was 0. And so in those cases, we had to think a little bit more. Remember, we had some, like if I said the limit as x approaches to x squared plus 3x. What do I want to do here? Minus 10 over x minus 2. Can I plug in the 2 there? No. So what do we have to do to evaluate that? Okay, we had to factor. We have not done the limit, so we are writing the limit. That is part of the problem. So this would be x plus 5, x minus 2 over x minus 2. Then those cancel. So we have the limit as x approaches 2 of x plus 5. And 2 plus 5 is 7. We had some where it was like the limit as a approaches 0 of a plus 3 squared minus 9 over a. Okay, can I just plug in my a? So what was my strategy? FOIL it all out. So a plus 3 squared means you have that 2 times, so that would be a squared. Then what happens?
Get rid of the 9s and then take out the
Right. So we have the 9s cancel. You can divide everything by a. Notice I'm writing my limit on every step. Then if you plug in 0, 0 plus 6 is 6. So we can get that limit. The final one that you really didn't like.
Square root.
Yeah.
You could just take the one from the book.
Yeah. This is not going to work out.
Radical.
Give me one out of the book. Let's
Radical.
see. You don't want me trying to wing this one.
X
It's not going to be.
25 plus, and then outside plus 9 over x.
It doesn't even have a radical.
No,
That's what he means outside.
What
X,
you have.
the radical x plus 25.
Radical x
Plus
plus
25. Plus 9 on the outside.
plus what?
Plus 9. I don't know.
What
Like-
about minus 5?
That works too.
I don't like.
Over x. And x approaches 0.
I don't like when Carson.
Okay. So can I just plug in my 0?
No.
No. So what was the strategy with a radical problem?
Conjugate. Conjugate, but make it weird. And then don't factor.
Right. So on the top, if I FOIL, the square root of x plus 25 times the square root of x plus 25 would be x plus 25. Because they're conjugates, outside and inside cancel. Minus 5 times 5 is 25. On the bottom, I'm hoping this x cancels, so I don't multiply that out yet. So we have the limit as x approaches 0. X over x times square root of x plus 25 plus 5. Now what happens?
My graph.
X is cancelled.
So that just gives us a 1, and now we no longer have a problem. So I have the square root of 5, or sorry, square root of 25, so 5 plus 5. We get So those are basically the 3 strategies that we did 2 days ago when we were last working on this. All right, are we okay with our recap?
Yeah.
And remember, if a limit is going to exist, the left and right hand limits have to match. We've talked about that from the graphs, from the tables. Same things are still true now. So I think, is this the next one that I have? I want to show that the limit as x approaches 0 of the absolute value of x is equal to 0. Okay, do I have a limit law for absolute value? No, so I can't just plug it in. But common theme with absolute values, we've already started doing it and we'll continue this whole year. Every time I see an absolute value, we are going to rewrite this with a piecewise definition. Okay, so think about what absolute value means. If x is a positive number, what does the absolute value give you? The same thing you put in, right? So if you do the absolute value of a positive number, it doesn't change. If your number is negative, what does your absolute value give you?
A positive.
So it does the opposite of what we put in, if we put in a negative. So if I'm going to check the limit at 0, since I have a piecewise definition, I'm going to have to do 2 separate pieces.
Wait, is the bottom one not equal to?
Technically, you could be equal to either one. It won't matter. So we're going to do the limit as we approach 0 from the right and the left. All right, if you are approaching from the right, that means you are plugging in things bigger than 0. So we are doing the positive case. So from the right is the greater than 0 case, so our function is just x. When we are approaching from the left, that's less than 0, so that is a negative x case. All right, but isn't x just polynomial? So our limit laws say we can just plug in. Whether you're approaching 0 from the right or left, when you go to plug it in, it's just 0. So if I replace my x with the 0, I get 0. If I replace this one with the 0, the opposite of 0 is
0.
So since these are equal, we have shown that the overall limit as x approaches 0 of the absolute value is equal to 0. And we should believe that. We know an absolute value graph is like a V as I'm coming in from, oh, that's really bad. As I'm coming in from both the left and the right, don't those go to the same point? Yeah, so we can see it from the graph as well. All right, let's try another. Let's think about this. So we have to do our 2 cases. Can x ever equal 0 in this? So we'll have a case if x is greater than 0 and if x is less than 0. All right, if x is a positive number, then the absolute value of x will just equal positive x, just x, right? If I put in a positive number, I get x out. What is x divided by x? 1. Okay, if x is negative, then when I do the absolute value, it's positive. So it's the opposite of what I put in, divided by the original number, so I would get negative. Okay, do we believe that? Let's think about it. So if x were positive, for instance, if I put in 5, the absolute value of 5 is 5. 5 divided by 5 is 1. If I put in negative 5, the absolute value of negative 5 is 5. 5 divided by negative 5 is negative 1. All right, so now if I go to do my limits, we have to do 2 separately. So we're going to approach 0 from the right and the left. So if I'm approaching from the right, that's bigger than 0, so which piece am I on?
The top one.
Top. So that's just 1. If I'm approaching from the left, that's less than 0. So that's my -1. Okay, but this is the limit of a constant. What's the limit of the constant?
The constant.
So this one equals 1 and this one equals
They all not trying.
they don't match. So those are not equal. So that tells me
It does not exist.
limit as x approaches 0, the absolute value of x over x does not exist. If we drew the graph on this, if it's bigger than 0, you're getting out 1. If it's less than 0, you're getting out -1. Do those limits match? No. So we can see it from our graph as well. I want you guys to try one. So here's a piecewise function. I already gave you the pieces. I want you to figure out if the limit exists, and if so, all right, we are approaching 4. So if I am approaching 4 from the right, that means bigger than 4. Which piece am I on? The top one. Okay. Can you plug in 4 here? So our rule is if it's a polynomial, we can just plug it in. But don't we also have a rule that says you can bring the limit under a radical?
Mm-hmm.
So if I did that,
Because it doesn't matter what happens at the point, it just doesn't.
now can I plug the 4 in there?
Yeah.
Okay. 4 minus 4 is 0. Square root of 0 is 0. So this limit equals 0. As we approach 4 from the left, my numbers are smaller than 4. So it's the bottom one. So that's polynomial. I can plug in my 4. 8 minus 8 is 0. So what does that tell me?
It does exist.
The limit exists. It is 0.
Would it have been okay if I didn't show that middle step of putting the limit under radical? Oh, okay.
I have a question.
Mm-hmm.
So on the first one, would you be very, very upset with us if we just put equal 0 to recognize that it can go?
You just need to be careful. If I had been doing the first one, would I have been able to do the limit as x approaches 4 from the left?
No,
Why?
can't have a negative.
Yeah. If I were plugging in a number smaller than 4, so if I put in 3.9 minus 4, I'm getting a negative under my radical, and then it would not exist. So you have to just make sure, especially when we're approaching from the left and right, that you're thinking about that when radicals are involved.
Okay.
So that's why we don't have a rule saying if it's a radical, just plug in your number. You have to think about it, especially if it's a one-sided one. Okay, let's do another one. What's that symbol mean?
So now there's another absolute right after right?
Double absolute value.
Oh, you guys have seen this before?
I know, I have no idea what this
Wait. Bracket on a bracket.
Mm-hmm.
is. Are you multiplying it by itself?
Nope, this was from Algebra 2 and
Oh.
college algebra. What is that function called?
So not pre-calc.
We did pre-calc.
Oh.
I don't know.
Matrices.
Grayson-Ger function.
What?
The stair steps. You guys have seen that.
Oh, with the circle and then the
Mm-hmm.
that's stupid.
What?
With the
Greatest
open
integer
circle and
function.
the closed circle and the open circle and closed
Oh
circle.
no.
What?
Oh, that's terrible.
The stairs of doom.
So, Grace
Oh.
integer function, remember, says whatever you put in, you only get out an integer. So if I put in 0, I get out 0. But if I put in a half, I can't get 1/2 out. But you can't get anything bigger than what you put in. So if I put in a half, I'm still getting out 0. If I put in 0.9, I'm still getting out 0. But when I put in 1, what do we get out?
One.
1.
So that's.
So remember, we're down here all the way to 1, so that's an open circle. Then we jump up. And so from 1 to 2, we'd be there.
Yeah, that's terrible.
This sucks.
The stairs of doom.
Oh, they're not that bad.
I'm gonna fall down the
guys are
stairs.
so dramatic.
That's what they all say.
They
People
say,
love us.
that's what they say until they fall down the stairs.
Okay, so remember this type of graph?
Yeah, why are the stairs full?
Okay, so as x approaches 3, what do you think the limit is?
3.
Probably 3.
Okay, let's see.
Oh, okay.
3.
Whoa.
I don't like that you said that.
Well, I don't want to see. What is it though?
No, because it's not going to 3 on both sides of 3.
Thank you. Somebody listens to me.
It's going on to
Okay,
3 on
if you put in a number bigger than 3, so if I'm putting in 3.1, what do I get out? 3. If I put in 3.01, I'm getting out 3. If I put in 3.001, I'm getting out 3. So this is equal to 3. As I am approaching x equals 3, so x equals 3 is right here. As I'm coming in from the right, I'm getting out 3 because I'm on this step. As we are approaching from the left, so if I put in 2.9, what am I getting out? 2. If I put in 2.99, 2. 2.999, 2. Because as you approach 3 from the left, you're down here on this step. So what's the overall limit?
Does not exist.
Does not exist.
Statement's a genius.
Wait, so
I'm a listener.
for me,
I was listening too. I'm just lost.
we put in it equals 2 because that's the closest to 3, right? Because like we could approach it from the left, like 1 is still like an option, but it's not. the
Right, you're
closest
doing
to
as
3.
close to 3 as you
Okay.
can get. All right, questions there? Okay, so the next part, I will probably do, I'll talk about it a little bit. Some things we can't do our limit laws for. Like we don't have limit laws, we've already kind of seen greatest integer. Do we have any limit laws involving that? No, we had to have some prior knowledge. Do we have any limit laws involving trig functions?
Oh, no.
No. So do we have any limit laws involving natural logs? No, so there's a lot of limitation to what we have so far. Sometimes you get really nasty functions that you cannot find a limit of. So here are a couple things to remember. If one function is always smaller than another, they're limits. The limit of the small one will be smaller. Does that make sense? I said that weird. So if
Does not make sense, no.
is less than g. Okay, so if I have two functions, f and g, and if f is smaller, so f is always on the bottom, then no matter what my limit is,
It can only be as high as the smallest.
the limit of f would always be smaller than the limit of g. Okay, limits aren't doing anything weird, it's talking about as we travel on our graph. If we extend that, if one function is in between two others, then its limit is in between the other two limits. That is what's called the squeeze theorem. And we can use that to evaluate unkind limits.
I thought it was like if they didn't agree, then the limit does not exist. Why is it like now that it's in between, the limit exists?
I'm not talking about like two pieces of the same function.
Oh, so it's like
What I'm
one
saying
whole
is,
function.
if like, I'm looking at g.
Okay.
G is in between f and h. So if I'm doing a limit of g, maybe I can't figure it out because I don't have any limit laws, but if I can do f and h, the answer to g has to be in between the two answers.
So we're gonna give an interval.
No?
No, we're just gonna find an example.
So,
What?
we're going to look at this one. We are going to be very limited in how much we apply this to right now, so we are only going to do it to similar functions. All the ones we do are going to involve sine and cosine. And I'm just teaching you the process right now because this is not something we will use a ton of. What you have to do is start out with a known statement. There is a reason we use sine and cosine. Because sine and cosine, if you're thinking about their graphs, what do they always fall between?
0 and or -1 and 1.
Right. Remember when we graph those curves, the lowest it can be is -1, the highest is +1. Everybody agrees with that.
Oh yeah.
Okay, so that is a known statement. So I can say -1 is less than or equal to sine x is less than or equal to positive 1. And we all know that. And I'm using sign because there's a sign up here. Okay? Now what I'm trying to do is get this inequality, the middle part, to match this complex thing right here. Now, when I say sign falls between -1 and 1, does it matter what the angle is? No, because remember, it's been a while, but in trig, that angle, it changed the period, like how quickly our graph repeated,
Okay.
but it didn't change the high and low points, right? So I can go from here and say, well, I really need this to be a 1 over x, but sine is always between -1 and 1, no matter what my angle. So the sine of 1 over x would also be between -1 and 1. Okay, so I've taken care of the sine of 1 over x. What else do I need in there? I need x squared. Okay. If we just multiply by a positive number, does my inequality change? Did my sign flip? Is x squared guaranteed to be a positive number?
Yes.
So would it be true that this inequality, I could just say, I'm going to take all of it times x squared. So that means negative x squared is less than or equal to x squared sine of 1 over x is less than or equal to positive x squared. Now these steps are the process. You can't just skip steps. This is like a proof. This is the justification. So any math-minded person should be able to pick this up and read from step to step and say, oh yeah, I agree with that. Sine is between -1 and 1. Oh yeah, doesn't matter what my angle is, it's still true. Oh yeah, I can multiply by an x squared, and this is still true. All right, so now we have all of this. What else do I need then?
Limits.
I need a limit. But the squeeze theorem said if this is true, then it's still true with their limit. So that's where the squeeze theorem comes in. So we are going to do the limit as x approaches 0 of all 3 pieces. Allowed to add that limit because of the squeeze theorem. But now we are in very good shape. We are. Can you do the limit as x approaches 0 of negative x squared?
Yeah.
Yeah, what is it? 0, it's a polynomial. Okay, we can't do the limit in the middle. We knew that. That's why we were doing all this work. What's the limit as x approaches 0 of positive x squared? Okay, so I know my limit has to be bigger than 0 and smaller than 0. So what's my limit?
0.
0.
What if you get an inequality where it's not 0?
It doesn't have to be 0, but
Like if it's not the same.
if
on
it's
both
not the
sides.
same, then it didn't help us. We could say it's between these values, but we don't know what the limit is
So
still.
our goal is to just get it the same on both
Mhm.
sides.
So our squeeze theorem problems, you'll be able to work them out like this, and it should be the same number on both sides. So then you know your limit is equal to that number.
Should be the same.
The problems I'm giving you are all, if I say use the squeeze theorem, it
It's just
works
should
with the
be.
squeeze theorem.
Okay.
Okay, so we're just working on that process. What I'm going to do is stop today. I will do another 1 or 2 squeeze theorem problems tomorrow. Another one for sure. We can do a second if we need to. Today, there is a handout posted on Google Classroom. It's like another 8 questions. So these are all limits that you should be able to either just plug in or factor and reduce. So these should work out. Tomorrow, we'll do our last squeeze theorem and then do the book problems, and it will be a work day after I finish that last example. Okay? Something that you might need on your homework, I think there is a perfect cube you have to factor at one point.
Oh,
So remember that formula.
it's